Module talks about accuracy and precision and how it applies to us in chemistry, in particular in the labs that you guys are going to be doing. So first, some definitions for you. Okay, this is what accuracy and precision are right here. Accuracy, how close a measurement, or if you take several measurements, their average is to the true value. We often measure this by calculating what's called the percent error. Now, that means, though, that in order to know how accurate a measurement or an average of a series of measurements is, we have to know what the true value is. Sometimes we do, sometimes we don't. Precision, you don't have to know what the true value is. All that's talking about is when you take several measurements, how close they are to each other. That's usually what we mean by precision. And the way we, a measure of precision is standard deviation, and we'll deal with this in the labs. So every instrument that you use to take any measurement in the lab or anywhere else, okay, has some limit to its precision. Let's say, for example, that you have a meter stick. Okay, let's pretend this is a meter stick. Okay, there's 0 meters, and over here is 1 meter, and there's marks every 1/10 of a meter or every decimeter. The rule is always that whenever you're taking a measurement, however far apart the smallest marks are, you always record one more place past the decimal in the number that you record. So for instance here, because the smallest marks are 0.1 meters apart, if you were to take a measurement with this meter stick, you would record 2 places past the decimal. Now that last number that you write, you're going to have to estimate it. So let's say we stop about, I don't know, right there or something, right? Let's see if we can make that smaller. No, I can't. So say about right here. Might be 0.63 or whatever you think it is. You have to estimate that 3. 0.62, 0.64 would have been both good numbers, right? And so there's a little bit of there is some uncertainty in that last digit that you write down, but it is still a significant figure. It carries useful information. So remember, one more place past the decimal than the smallest marks are. So let's measure some things. Okay, so let's say this tablet, okay? And this meter stick here, this is a meter stick, and each of these marks is a 1/10 of a meter, or 1 decimeter apart. So that means because just like that meter stick I drawn for you earlier, each of these marks is 0.1 meters apart. When we record a measurement that we take using this meter stick, we're going to write down 2 places past the decimal. So there's 0, there's 0.3 meters. So where is it here? Well, I'd say it's less than halfway. What do you think? Maybe 0.33, something like that. You're guessing, right? Make your best estimate. So let's call that, 0.33 meters. It's not showing up. As it happens to have 2 significant figures in it, but the important point is that the last significant figure is this second 3 right here. 2 places past the decimal because the smallest marks are 1 place past the decimal apart. Let's say we measure that same thing, same tablet, with another meter stick. Now here, okay, it says 1020, but that's really a 1/10 of a meter. It's 10, centimeters. That's 0.2 meters, 0.3 meters, okay? There's 0.33 right there. It's a little bit past that, isn't it? So what do you say? Again, we're estimating, but I'd say maybe 0.335. Again, if you said 0.334, something along those lines, it's perfectly fine, right? So here, the last significant figure is 3 places to the right of the decimal. The last significant figure in this number is the 5, because the smallest marks are 2 places past the decimal apart. 0.01, well, I'm not looking at the halves for here, but 0.01, 0.02, 0.03, up to 0.1 meters, or 10 centimeters. Okay, so we write 3 past the decimal. So if we're comparing those 2 meter sticks that we just used, what we can say, this is another way of talking about precision, the meter stick with the smallest marks closer together was the more precise tool. The measurement that we got from that it was a more precise number, meaning that its last significant figure was farther to the right in the number. And so we can say that when we're looking at a number, any number that came from a measurement, the farther to the right in that number the last significant figure is, the more precise that number is, or actually the more precise the tool was that was used to take that measurement. Now, let's say, okay, we are trying to aim at this red dot in the middle right here, and these green dots are where we hit. So we're throwing darts or tennis balls or something at them, right? And the analogy that we're making here is to a series of measurements that we make in the lab. So this red dot would represent the true value. Let's say we were trying to figure out how much something weighed, and that represents the actual mass. We took 3 measurements. They were very, pretty close to each other, and that means those 3 measurements are precise, but they're not very accurate because the average of these 3, which is be right about in the middle of them, is not very close to the middle of the bullseye or the true value. So we can have measurements that are precise but not accurate, just like this. On the other hand, we could have measurements like this, okay? These are not very close to each other at all. They're really spread out, so they're not precise at all. However, if we were to take the average of these measurements, it's going to be somewhere pretty close to the true value, the bullseye right here. So what we could say is these measurements are accurate but not precise. Ideally, right, whenever we take a series of measurements in the lab, we would prefer them to be both accurate and precise. So real close together and right on the true value. It's possible, because this is the worst case scenario here, we could have measurements that are not accurate because the average of those is not close to the true value, and not precise either because they're fairly widely spread apart. Again, we want precise and accurate if we can.